Okay, so today we are going to focus more on respiration. I know we started it last week. And in case you all didn't remember, respiration is how the body creates energy. Remember, every living organism, whether it be an animal, whether it be a plant, it needs what? It needs energy. Okay, so quickly on the chat, who can tell me what two ingredients are needed for energy? Let me just pause. So the question once again is, your body needs energy. What are the two things your body needs in order to create energy? Now, if we went back to this slide over here, let me enlarge it here. Look at this slide now, and you will see why most of you all are wrong. In order to create energy, your body needs two things. The two things are glucose and oxygen. That too many people got that wrong, and we had spent a lot of time, discussing that last week. Okay, so these are the two items needed. For the first part of class, we're going to concentrate on oxygen. How does the body get oxygen in the first place? And of course, once the body gets the oxygen, it can do what? Create energy. So let's move ahead. Let me just pause it here and move ahead to where we were. All right, so this is where we are at now. So it seems that we need to get oxygen into the body. And of course, what the part of the body that you may be familiar with that is responsible for at least the first part of getting oxygen is the lungs. Because when we breathe in, we pull in air. And of course, air contains oxygen. But once the oxygen is in the lungs, we have to discuss how the lungs will extract that oxygen, because air contains a lot of things. One of them just happens to be oxygen. And once it extracts the oxygen, we have to get it into the blood stream, right? And we're going to discuss that in a little while. So I want everyone to look at the diagram in front of us. Let's take a look at. Let's go through, of course, protecting our lungs is our ribs, well, part of our skeletal system. Now, let me just go through some basic parts of the lungs here, and then you're going to take your time and, try to draw the diagram out. First of all, there are two ways to breathe, right? You can either breathe through your nose, or you could open your mouth and breathe in. Now, I'm going to skip that part. I think everyone at least knows that, right? However, when you breathe in, the air comes through a narrow channel, right? That's kind of at the center of your chest. We usually call it our windpipe, but its real name is the trachea. Obviously, I can't call it the windpipe in the exam. You got to use the technical words. So the air comes down into our trachea, and then it goes down and down. Then the channel splits into two. Now, there's a good reason it splits into two. Our lungs has two sides, a left side and a right side. Obviously, you want some of the air to go to the left, and of course, you want some of the air to go to your right. Now, the first split after the trachea is called your bronchus, right? Now, when it goes over here, you notice it splits into what? Smaller pieces. It's like a tree. A tree has a main branch, and on that main branch, it might have smaller branches, and that smaller branch might even have smaller branches coming out of it. So when the bronchus splits into smaller pieces, right? You notice the little orange lines here. That's called the bronchiole. Okay. Now, when that happens, it eventually goes into these small little bubbles. The bubbles, well, are called the alveoli, that's plural, and the alveolus is what? Singular. Some of you all might be confused about this thick red line. I'm not too sure if you all ever realize this, right? If you put your hands on the upper part of your stomach and you breathe in and you breathe out, yeah, and you kind of like push your hands to the upper part of your stomach, you will feel a kind of muscle moving, like, well, it kind of moves up and down. Whenever you breathe, right, this muscle called the diaphragm, normally it is be curved upwards. Normally, like when you're doing nothing, like let's say you're not breathing just for a few seconds, your diaphragm will be curved upwards. But when it's time to breathe or pull in air, you will pull down that muscle. Now, here's the thing, right? A lot of people get confused about the states of a muscle. Whenever you are doing nothing, let's take a more familiar muscle, your biceps, where your arms are. Let's say you are doing nothing. So your hands free, you're just hanging downwards. Whenever you're doing nothing, you call that a relaxed position. Your muscles are relaxed. But the minute you take your muscles and try to do something, like lift something, that's called the contracted position. So when you are doing nothing and your diaphragm is relaxed, it is naturally curved upwards. But when it's time to breathe, you contract the muscles and you pull it downwards. All right. Also, what you need to know is that your ribs, in between your ribs, you have some muscles in between. And you can probably take your fingers and probably kind of push it in between, not too hard, obviously, in between your ribs. And you'll feel like a kind of muscular structure over there. Those are your intercostal muscles. And of course, I'm going to show you how the diaphragm and how your intercostal muscles work together to get air inside your body, and of course, push out the air when it's necessary. I'm going to give everyone 5 minutes to draw both diagrams, label it to the best of your ability, and let me know when you are finished. Right, so let's move on. All right, so quick question. I think everybody knows a little bit about pressure. We're going to talk a little bit about air pressure. And the question is this. Have you ever thought at any point in time when you were so bored how air actually enters your body? Like when you decide to breathe in, I know some muscles will move in your body. But you ever sat down and asked yourself, why does the air actually move into your body? Or when it's time to breathe out, why does the air move out of your body? How much of you have, honestly ever considered that question? Or do you just take breathing for granted? You open your mouth, you pull in. You want to expel air, you just push out the air. Right? So in case you were ever bored like me, or never bored like me, or whatnot, however you want to look at it, I'm going to explain that concept to you all. The first thing you have to remember, or to get a grasp of, is pressure. Which part of your house right now, you can actually find it in your kitchen, name something that has high pressure in it. Take a guess on the chat. Name something in your kitchen that has high pressure in it. All right, and most people are going to say your gas tank, correct. You know that gas tank, it is connect to your stove. There is gas, obviously, in the gas tank. And I think everybody by now knows that the pressure inside the gas tank is supposed to be high. But tell me something. What would happen if there was too much pressure in the gas tank? What dangerous thing could happen? It could explode, right? If there's too much gas inside the gas tank and the pressure is too high, it can actually cause the gas tank to explode. The point is, right, what I'm really trying to get at, things could either be at high pressure or things could either be at low pressure. So that is what this note is about. You'll see I'm using the terms high and low pressure. Now let's talk about movement. Let's use our imagination here. Let's say we have 2 points here, point A, and over here is point B. Let's just say over here, there's a lot of air. Well, we use a different color there. We use black or something, right? So let's say there's a lot of air particles at point A. And I just tell you that at point A, the air is at high pressure. And at point B, I'm just going to put a little less particles, right? But the point is, at point B, there is low pressure or lower pressure. How will the air particles move? Look at the note on top here. Will the air particle move from A to B, or will it move from B to A? Which direction do you think, based on the note, it will move? And I think most people are getting it correct. Air, or not only air, almost anything in nature always moves in this particular direction. It always moves from high towards the low. So since the pressure at A is high and the pressure at B is low, the air particles will move from A to B. As simple as that, right? That is what we call a passive process. I would have used that word last week, meaning that without you doing anything, the air will naturally move from high pressure into low pressure. Next, you don't have to take down anything there as yet because I have the note over here. But let's talk about what makes the pressure high and what makes the pressure low. I mean, I think that's an important part of the conversation. I just can't come and tell you over here have high pressure and over here has low pressure. I'm sure the question in your head is, what could possibly make the pressure high? So I have two containers here, right? I'm just going to call it container A and container B. Let's say in container A, I have 5 particles of air. In real life, you're going to have much more, right? You're going to have millions and, well, not millions, trillions and trillions, but I don't have time to draw a trillion today, probably next week. Now, in container B, I am going to put the same amount of air particles. It's still 5. So I'm just going to put 1, 2, 3, 4, and 5. Which container, now whenever you put air into something, it will increase the pressure. Which one will have the higher pressure, A or B? You can read the note and figure it out. I should not have put the answer on the screen, but laziness, I guess. Right, and the correct answers are, well, only one person got it wrong, right? The larger the volume, let's read this note. The larger the volume, the lower the pressure. Normally, You see, what some people are doing, they're associating larger containers with larger pressure, but that it's actually the opposite. The smaller the container, the higher the pressure, or the larger the pressure. So container A will have a high pressure. Container B, because it is larger, it actually has what? A lower pressure. Okay, so for those who got it wrong, you understand it now. I mean, it's a concept you probably just have to get out of your head. You have to stop associating larger containers with a larger pressure. It's actually the opposite of what you would normally think. I want everyone to take down everything on the screen, and I'm going to be saying it over and over for a little while. The smaller the space, in other words, the smaller the container, the higher the pressure. The larger the space or larger the container, the lower the pressure. Let me know when you are finished. So let's see what's next on the list here. And let's see what this having a larger volume and a smaller volume has to do with breathing. What does it have to do with getting what? Air into our body or getting air to leave our bodies? That's some technical difficulties here. All right, so here's where we are, right? Our atmosphere, right? Where you are sitting right now, there's an atmosphere around you. There's an atmosphere around the earth. Now, the atmosphere itself has air in it. Well, obviously, the atmosphere has air. That's where we get our air from. Our atmosphere has a certain pressure. Now, in case you didn't know, pressure is measured in something called pascals. The symbol for pascals is PA. Just like how you can measure mass in kilograms or grams, or you can measure time in seconds and hours. Well, if you are measuring the pressure of something, the unit for it is pascals. You all are seeing a capital K here. Capital K just means to multiply it by 1,000. The K stands for kilo, like kilograms, okay? Our atmosphere around us right now is roughly 100,000 kilopascals. In other words, our atmosphere right now is pressing down on you at a massive pressure, 100,000 pascals. That's a lot, by the way. It's just that we don't feel uncomfortable because our bodies are made to be accustomed with it. It's strong enough to resist 100,000 pascals. Here's what's going to happen now. When you are doing nothing, I'm talking about you relaxing. You're not breathing in, you're not breathing out. You're in between breaths. The pressure outside your body is 100,000 pascals. Normally, right, your diaphragm just be upwards like this. Remember, there are two positions. So I want you all to pretend that your diaphragm is relaxed. When it's relaxed, the pressure outside and the pressure inside your lungs does be exactly the same. So tell me something. There's air outside and there's air. Obviously, there's always a little bit of air inside the lungs. If outside is 100,000 pascals and inside your lungs is also 100,000 pascals, how will the air move? Will the air move into your body or will it move out of your body? What do you all think? What are your thoughts on that? Quick question. Remember, air moves from high to low. But in this first scenario, right, what happens is that the air outside and the air inside is the same. So that means no air pressure is higher than the other. So that means since outside and inside don't have a pressure difference, nothing happens. The air doesn't move out and the air doesn't move in. For those who got it wrong, you understand that now? That because outside and inside your body has the same air pressure, none is higher than the other, the air doesn't move in any direction. It stands still. For those who got it wrong, let me know that you're on. You don't have to make a note yet. I just want to make sure you're on the right track of understanding, that you understand that the air does not move. But here's the thing now. Eventually, right, what's going to happen is that when you want to breathe in, you're going to pull your diaphragm downwards. Now remember, the diaphragm was curving upwards. So there was a certain space here. When you move it downwards, does the space get larger? I'm talking about the whole inside of your body where the air has to be. So if I move this downwards, did the space get smaller or did the space get larger? The space got larger, right? Now, when you pull it downwards, I just want to put the arrow here. The space got larger. Remember, the air pressure a few seconds ago was 100,000. So if the space gets larger now, the overall average space, will the pressure get higher or will the pressure get lower? Go back to the notes on just the last slide. Whenever the volume increases, whenever the container increases, right? So a few of you all are getting it wrong, but remember we said the larger the space, the smaller the pressure. So when your diaphragm moves downwards, right, the space gets larger and the pressure gets smaller. Now I'm making up a value here, right? The point is 90 is less than 100, okay? So that means if outside we call it A and inside your body we call it B, how will the air move now? Will it move from A to B or B to A? Right, remember pressure always moves from higher to lower. So that means since outside is higher and inside is lower, the air is going to come into your body. And that's the science behind it. In order to get air into your body, all you're trying to do is make the air pressure inside your body smaller than outside. And once our inside is smaller, the air will naturally flow from outside, which is higher, to inside, which is lower. Now, let's say you want to get the air out your body. Well, guess what, right? When it's time to breathe out, your diaphragm will move upwards. And of course, when your diaphragm moves upwards, right? But when you kind of push it up against your lungs, it will make the space much smaller. Look at it, the space in between here is going to get smaller. And of course, when the space gets smaller, the pressure will get higher. So let's just call it 120, all right? They're just for simplicity, right? Now, because you made inside your lungs area, that general area, smaller, the pressure gets higher. So now the air has to move from high to low. So it will flow out your body. All right. So, and that's really, really important, right? Now, I just want to check the next slide just to see if I have this summarized, right? Let me just check it. All right. I'm not going to ask you all to draw this here, right? Just 1 second. I'm not going to ask you all to draw this diagram. This is going to be a little too complex. In the table after, I kind of summarized everything. Right. So just to summarize quickly before we move to the table. When you're breathing in, your diaphragm moves downwards, the space increases, right? And the pressure drops inside your body. When it's time to breathe out, your diaphragm moves upwards. It decreases the volume, hence increases the pressure, and the air flows out. So let's move to the table here and let's discuss the values on the table. How many values are talking about the notes on the table? So we're going to discuss the differences between breathing in and breathing out. When you inhale, in case you didn't know, inhale means to breathe in. If you breathe in right now, like take a real deep breath, you will notice that your ribs move upwards and out. You can try it now. Just put your hands on your ribs and take a real deep breath in. You will notice that your ribs will actually move upwards. And of course, everybody knows from practical experience that your ribs will move outwards to make the space larger. Your diaphragm will move flat. We just discussed that. This causes the chest volume to increase. Hence, the pressure inside the chest decreases. Remember, pressure and volume are opposites. If volume is large, the pressure will be smaller, and of course, vice versa. Now, when you exhale or breathe outwards, the opposite is going to happen. Your ribs will what? Move downwards and in. The diaphragm moves up into the chest cavity. In other words, it gets back curved. The chest volume will obviously decrease, but the pressure inside the chest increases. Read through the table, make sure it makes sense first. Then copy it down and then let me know if you are finished. On here. Let's see if something more exciting is on the next slide. I don't know what's going on with this wheel here. Oh. All right. Now, the thing about it, there is a difference between the quality of air when it's coming into your body and when it's coming out of your body. Now, a lot of these, this table could actually be derived, a lot of it could be derived from common sense. Let's go through each one by one here. It won't take too long. When you are now breathing in the air, there will obviously be more oxygen. Roughly about 20, different textbooks is going to have slightly different values, right? Some textbooks will have 20%, some of them will have 19 or 18%, right? Let's just call it 20%. So when you're breathing in air, you are hoping that the air has a lot of oxygen, and 20% is a decent amount. Now, obviously, when you breathe in the oxygen, which is in the air, your body is going to steal that oxygen because the body wants oxygen. So when you're breathing out, you notice some missing. How much percentage it went missing? If you breathe in 20 and only 16% come back out, how much oxygen did the body steal from the air? What percentage? Simple calculation, not a trick question, right? It's just 4%, right? So in other words, whenever you breathe in, your body only steals 4% of that oxygen, right? I know what you're saying. Why doesn't your body just steal all the oxygen? Well, why doesn't it just steal all 20% and get it over with? Your body is like a sponge, right? Every sponge has its limitations. Like if you have too much water, no matter how hard you try, a sponge in one try can only pick up a certain amount of water. The same thing goes for your body and oxygen. It would have been incredible if your body could always steal the amount of oxygen that's in the air. That means you will have way more energy in a case like that, right? But you don't. Let's talk about carbon dioxide. Whenever you are breathing in, first of all, carbon dioxide is not good for the human body, but there's carbon dioxide in the air right now in front of you. And lucky for us, there isn't too much. It's only about 0.03%. But when you breathe out, do you all remember when your body performs respiration? You just get three major things. There are four, but I only want to concentrate on three. You just get three things: water, carbon dioxide, and energy. You want the energy, but you don't want the water and carbon dioxide. So when you are breathing out, you see all that carbon dioxide that was created in your body via respiration, your body will try to get rid of it, and it will send it to your lungs. And when you breathe out, that unwanted carbon dioxide will exit your body. So when you're breathing out, you actually have more carbon dioxide coming out than coming in. The other gases in the atmosphere, like nitrogen, and have a few others like helium and hydrogen, your body doesn't need it. So when you breathe in or you breathe out, the same amount comes in and the same amount comes out, right? Your body isn't too concerned about the other gases. It only really cares about the oxygen and the carbon dioxide. Water vapor. Remember, during respiration, water is created. Last week, I told you that water is basically bad water. It will end up in your lungs, and when it reaches in your lungs, you need to breathe out to get rid of that water. So when you breathe in, it usually has less water vapor, but when you breathe out, you have more water vapor. The term I want you to memorize is saturated. Saturated means that the air that is coming out has its maximum amount of water vapor. Just remember the term. The term saturated just means it's filled, completely filled to capacity with water vapor. And I think everyone knows this one here. When you breathe out, right? When you breathe it in, air is usually be cool. Let's just assume it's a normal day. But when you breathe out, like when you breathe out into your hands, doesn't it feel warmer? That is because when you breathe out, the air coming out is be at the temperature of your body. And there's good reason for it. It just left your body. So obviously it's going to have the same temperature as your body. Take down the table. Let me know when you are finished. All right, so to answer the question now that a few people did ask. So we have the oxygen in our lungs. Good, not a problem. We need it in our lungs. But that oxygen needs to what? Get into our blood, okay? That's super, super important. Because once it reaches our blood will transport that oxygen to our cells. And once it reaches our cells, there's a particular part of the cell that will take the oxygen, mix it with glucose, and give us energy. On the chat, what's the name of that part of the cell that combines glucose and oxygen to give us energy, which is called respiration? Which part of the cell performs respiration? Right, and I love the answers I'm getting here. It's called the mitochondria, right? The big long M word, right? The mitochondria. But we have to talk a little bit about dissolving. Now, I think most people know what dissolving is. And the most common example of the dissolving is that if you take water and you put salt or sugar in it, and you take a spoon and spin it, and we normally say, hey, the salt or sugar gets dissolved in the water. But why is dissolving something important to this conversation? Let's take an example here, right? We have 2 glasses of water here. Instead of water, let's pretend this is blood, right? So in both instances, you have what? Blood. I should have chosen a diagram with red in it to simulate the blood, but I couldn't find a free diagram. Let's say instead of oxygen, let's talk about salt. And we rest a napkin on top of the glass, right? So nothing can actually reach directly to the quote unquote blood. If I want to get what? The salt into the blood, tell me if this is a good idea or not. I take dry salt and I sprinkle it on top of the napkin. So I just sprinkle it. Will the salt end up in the blood? What do you all think? The answer is no. That's madness, right? It's not going to reach into the blood, right? First of all, the salt cannot soak through the napkin because it's dry. But if I take the salt and put it in water and dunk it on top of what? The napkin. Now, provided that the napkin is a strong napkin and it doesn't fold into the water, right? Do you think if I dissolve the salt and then put it on the napkin, do you think that the salt and the water, the point is, the salt, do you think the salt would make it to the other side, into the blood? What do you all think? I think in a case like that, it would make it into the blood. So in other words, if there is a barrier and there's blood underneath, and I want something from on top to reach into the blood, we should dissolve it. That is what I'm getting at, right? So dissolving something makes it easier to go through a barrier. And the barrier in this case is the napkin. Now, instead of directly just dunking the salt in water, I have a different solution. How about we take this napkin and we drench it in water, so it's a wet napkin, like real super wet napkin. If I put dry salt on it now, do you think over time the salt will make it through? Well, what do you all think? Do you think it's possible? I think yes, it is possible, because the napkin is super wet. Well, when you throw the salt on it, the salt will dissolve, and of course it will slowly what? Seep through, and some of it will make it into the blood. That is going to happen when I start to explain the lungs. Instead of salt, we're going to use what? Oxygen. It is possible to dissolve oxygen. It's just that nobody does normally talk about it. When you hear the word dissolve, you just think only salt and sugar. But you could dissolve oxygen. Believe me, you can. Okay? Right. Now, look at the second diagram, right? Let's say this is a thicker napkin and we make it super wet as also. And we sprinkle salt here as well. Now remember, this napkin is thicker, this napkin is thinner. I'll call this A and I'll call this B. Which one, in which scenario, will the blood have more salt? We're looking for the diagram that will have more salt inside the blood. The answer would be A, right? If the napkin is too thick, that means the salt, even though it dissolves, is going to take longer. It's going to have a harder time to move through the thick substance. Okay? We're going to put all of that together now. So when we're talking about the lungs and air moving from the lungs into the blood, we should see something being wet or moist. That seems to be very, very important. Also, if there's a barrier, we are hoping that it's very, very thin, because the thinner it is, the more oxygen can move across. Also, would you like the napkin to be large? I'm talking about the surface area, right? Would you like the napkin to be large or the napkin to be small? Which one could hold more salt? You want a large napkin, because the larger the napkin, the more salt can fit on it. And of course, the more salt that can fit on it, the more can soak through at a time. So it's three things we're going to look for in the lungs, and three things. We're going to make sure that at some point, some part of your lungs is wet. We have to make sure that the barrier inside your lungs, the barrier in between your lungs and the blood, has to be thin. And also, the barrier has to be large. We don't want small, thin barriers. We want flat, large barriers. There's no need to take down anything here. I will summarize this in a little while, okay? Right, so this is the diagram over here. Who go back to the diagram of the lungs, and who can tell me this here is the last part of your lungs? Remember how the air comes into your mouth? It will go into your trachea. After your trachea is the bronchus, then the bronchiole. But what's the last part and the smallest part of your lungs? Look back in the diagram, guys. And that is going to be an alveolus. Well, plural is what? Alveoli. What has happened? This green dot over here is going to represent Mr. Oxygen. So the oxygen came in through your mouth or nose, and it made it to the end of the lungs, which is the alveolus or alveoli, right? So the oxygen is here, and touching on the right on the outside of every alveoli, there's a blood vessel running. And this blood vessel is connected to our cells, right? And inside our cells, it have the mitochondria, who is ready. He's hungry for oxygen. He's just waiting for oxygen to be delivered to him. So what's going to happen is that the oxygen has to make it across into the bloodstream. You will notice that the barriers here, and I'll try my best to draw it thin. The barriers is supposed to be what? Thin. And tell me something. The oxygen, can it just move across, or do we have to dissolve it first? Remember the scenario with the salt. Is it okay for dry oxygen, or do we need wet, dissolved oxygen? Which one do we need, dry or wet, dissolved oxygen? We need wet, dissolved oxygen. So a lot of people don't know this, but inside your lungs always has a certain amount of water, a certain amount of moisture. Now, it doesn't have enough to drown you, but the ends of your alveolus it has water, moisture on it. And you know why this is important, right? So that blue part there is moisture. Hope I spell it correct here. Any spelling errors, I'll rectify that later. So when the oxygen comes in, it's going to touch the water, the moisture. It's going to dissolve. And when it dissolves, it can move across into the bloodstream. Now, if the examiner asks you, how does it move across? Now, we know it gets dissolved. I think we understand that. But what's the name of the process after it gets dissolved and move across? You just call that diffusion. It will diffuse across the barrier into the blood. And remember last week we did diffusion, right? Notice how big the alveoli is. The shape of the alveoli is this. The shape of the alveoli is not this. You know why? A circular shape has more space than a V shape. So remember the talk about the napkin, that we wanted a large napkin. We don't want a small, skinny napkin. We want a large, kind of spread out napkin. Okay? Right. Here's what I need for you all to do. Draw this down. The cell, you don't have to draw this complex cell, right? Just draw a circle and call it cell. But I need the diagram of the alveolus, the blood vessel touching it. And by the way, whatever the cell does not want, things like carbon dioxide. Remember, here's what? Carbon dioxide and water. Carbon. So I'm going to spell out better for you guys. You have what here? Carbon dioxide, and you have what? Water. These are things that the cell does not want. So they will go the opposite direction. So the good things coming in and the bad things leaving. This general area over here, right? Well, where there's a kind of crossover from the alveolus or alveoli into the what? The bloodstream, right? That general area is called, and I'll write the words just now, a respiratory surface, right? So this general area is a respiratory surface. Now, all respiratory surfaces, like anything that's breathing or needs oxygen in its body, usually has certain traits for it to be efficient. So let's take a look at the next slide here. So here's the word, a respiratory surface. And we discussed most of these things already. For something to be classified as a respiratory surface, this goes for almost any living organism, right? Except for plants, right? Talking about animals in general. Do you all agree with one? Did we discuss part one? That respiratory surfaces need to have what? A large surface area. This is to allow as much oxygen to be captured as possible, right? So that's this area over here. The respiratory surface must have a large surface area. We also said that they must be as thin as possible. So that being thin means whatever gets dissolved can move across easily. We saw a thick napkin can prevent things from moving across. We want a napkin to be thin. We need all respiratory surfaces to be moist. Being moist means it can dissolve things like oxygen. And when things are dissolved, it can move across very, very easily. There must also be gases involved. But the gases involved in today's question is mainly oxygen and carbon dioxide, right? It doesn't make sense to breathe if there's no oxygen available, right? And also, all respiratory surfaces must have a blood supply very, very close to it. Because what's the point of breathing if it's not going to take the oxygen and put it into the blood? It needs to reach the blood. So in the exam, in summary, the examiner loves to ask, what are the 5 traits or 5 properties of a respiratory surface? And you have them now, right? So take it down. Let me know when you are finished. You don't have to draw the diagram. You already have the diagram. All right. So, we're going to talk a little bit more about respiration. Now, at the bottom of the screen there is something that you've been seeing since last week. When we talk about respiration, we normally think about the mitochondria, and of course, it will mix glucose and oxygen. And when you mix those two together, we get carbon dioxide, water, energy, and heat. But like I said, most textbooks will leave out the heat part. There are different types of respiration, right? There's actually two main categories. One called aerobic respiration and one called anaerobic. Whenever you hear the word aerobic in any science class, aerobic means that there's oxygen involved. So the type of respiration the only type of respiration that we have talked about so far involves oxygen. Hence, this type of respiration is called aerobic respiration. But your body can actually produce energy without oxygen, but it only does it as a last resort. Like if the body can use oxygen, it will use it. But let's say all the oxygen is finished, your body has a backup plan, but the backup plan doesn't work forever, right? Just take down the item in red, everything in red. I know you have this formula already. Take it back down again and make a note that this type of respiration, because it involves oxygen, it has a special name, aerobic respiration. Right, so take a few seconds there and let me know when you are finished. All right, so I think the next slide will obviously concentrate on the other types of respiration. So let's have a look and see what the other types of respirations are. Right, so this is what normally happens, right? You take oxygen and glucose and you get what? 4 things: carbon dioxide, water, energy, and heat. It's the same equation down here. Now, the opposite of aerobic respiration is what? Anaerobic respiration. So, but there are 2 types of anaerobic respiration. Now, anaerobic respiration means that oxygen is not involved. At no point in time in these equations, you are going to see oxygen. So let's talk about anaerobic respiration that occurs in animals. Now, remember, I told you human beings are considered animals. Let's just say that you're running a race. You know, sometimes you're running a race and at some point in time, you get so tired that you're out of breath and you just can't breathe fast enough. Whenever that starts to happen, right? Let's say that you can't breathe fast enough. That means your body is not getting enough oxygen. Of course, your body is trying to get more oxygen by breathing faster, but you just can't because your body has limitations. So that means at that point in time, your body not getting enough oxygen, so it cannot perform normal aerobic respiration, but it needs energy. Otherwise, you're going to fall down and die. So here's the backup plan. Your body says, all right, you don't have enough oxygen. The body is going just to take the glucose. Look at this. It takes glucose directly. It has no oxygen involved. And your body will turn the glucose into two things: lactic acid and energy, which is good. I'm talking about the energy part is great. Your body needs that. But it creates this thing called lactic acid. Do you all think that that lactic acid is good or bad for you? What do you all think? It's bad, right? Lactic acid is bad for your body. It's toxic. Too much of it can actually kill you. So that means whenever your body performs anaerobic respiration as the backup plan, you get energy, but you get this bad thing associated with it called lactic acid. For the time being, let's just say that lactic acid is bad and your body will need to get rid of that lactic acid. Because if that lactic acid stays inside your body too long and it builds up to a dangerous level, you will die. How does your body get rid of the lactic acid? I don't think I would reach that part today. I might start on that next week. All right. So in plants and yeast and bacteria, sometimes there's no oxygen available. So some plants, yeast and bacteria have a backup plan. They can also create energy using anaerobic respiration, but they do it a little bit different. They will take the glucose and they will convert it without oxygen into three things: ethanol, carbon dioxide, and energy. The energy is the good part. Carbon dioxide and ethanol. Carbon dioxide is bad. Do you all know what ethanol is? Anybody want to take an idea of what ethanol is? It's something that people can buy in the grocery, but we call it by a different name. Ethanol is consumable alcohol. I say the word consumable because there are many different types of alcohols. Some are more dangerous to humans than others. I mean, alcohol on the whole is dangerous, right? But you can actually consume this type of alcohol. This is the type of alcohol found in rum and beers and whatnot, right? But there are many other different types of alcohol other than ethanol that have things like pentanol or methanol, which are way more dangerous to human beings. So guess what? This is actually how they make alcohols, like how you say, like Carib and Stag and all the other places, like, oh God, Angostura and whatnot, right? This is how they make consumable alcohol, you know. They use anaerobic respiration and they use a particular type of yeast, and that yeast will take glucose and convert it into these three things. But they will extract the ethanol. Of course, once they extract the ethanol, they put it in beverages and then they sell it. All right. So in the exam, you have to know both types of anaerobic respiration and you have to memorize the formulas, right? One is for animals and the other one is for plants, yeast, and bacteria. Right? There is no difference in names with the types of anaerobic. It's just one type of anaerobic is for animals and the other one, which is a slightly different formula, is for plants, yeast, and bacteria.